We're sketching the cosmic web in 3 dimensions, one of the largest sky maps ever attempted. I like beginnings that arrive as a simple line and then quietly open into scale. Tonight I want to sit with a cartographer's thought, that the universe can be tiled patiently, field by field, until a picture emerges, not a flat picture, but a layered atlas in depth and time. And the reason to speak now is that the European Space Agency's Euclid mission has just laid its first true tiles for the world to examine. The quick data release, published in mid-March of the year 2025, with a first glimpse of the deep fields. It is a modest-sounding phrase, quick release, but it contains millions of galaxies and a preview of the long map to come. Euclid is a purpose-built cartographer of the dark, a telescope designed to measure with exquisite uniformity how structure grows across the sky and through cosmic time. Its job is to weigh the influence of dark matter, the mass we do not see, and to trace the pressure of dark energy, the thing that drives cosmic expansion to accelerate. To do this, Euclid leans on 2 complementary probes. The first is weak gravitational lensing, the tiny, coherent stretching of galaxy images by foreground mass. The second is the statistical ripple we call the baryon acoustic oscillation, a gentle standard ruler embedded in the distribution of galaxies. Together, they allow us to draw the 3-dimensional web and ask how fast it grew and why. The first quick release is a promise kept rather than a verdict. It covers just over 63 square degrees, several hundred times the apparent area of the full moon spread across the Euclid deep fields, in the north, in the south, and toward the Fornax region. In those tiles live roughly 26 million detected sources, with images from the visible camera, images and slitless spectra from the near-infrared instrument, external ground-based context, and carefully prepared catalogues. It is not yet a cosmology result. Think of it instead as the first pages of a field notebook, the part where you test your pencils, but you can already see the hand. If you page through the release images, you meet the purpose. There are strong gravitational lenses, a foreground galaxy wrapped in a halo of dark matter, bends the light of a background system into arcs. There are delicate disks and tidal streams, and clusters sitting like knots in a fishing net. In the deep field preview frames, hundreds of thousands of galaxies seem to float in layers. You can almost feel the parallax of time as you scan from one faint smudge to the next. These are not just pretty photographs. They are raw material for a census, the clay from which we will extract shapes, colors, and distances for enormous numbers of galaxies. Euclid makes these tiles with 2 instruments that work in concert. The visible imager, called the visible instrument, captures sharp, broadband optical images with a focal plane of roughly 609 million pixels and sampling around 1/10 of an arc second. It is built to measure shapes, because weak lensing lives in tiny distortions that average out only when you have measured them for countless galaxies. The near-infrared spectrometer and photometer supplies the vital depth, imaging in near-infrared bands to constrain colors, and slitless spectroscopy to recover redshifts for a vast number of sources, so that the flat sky becomes a volume. It is a simple idea. Measure positions on the sky and distances along the line of sight, and the 2-dimensional panorama becomes a 3-dimensional map. But to make it precise across 1/3 of the sky and over 10 billion years of look-back time, you need instrumentation that does the same thing, the same way, everywhere. That is Euclid's character. There is a cadence to this cartography. Euclid began its wide survey on the 14th of February in the year 2024. Within a month, it had already overtaken the total sky area imaged by the Hubble Space Telescope across more than 3 decades, a reminder that uniformity and area are themselves profound forms of depth. The timeline now stretches ahead in planned milestones. This first quick installment in March 2025, a second quick release in late June 2026, the first comprehensive data release in late October of the same year, and further waves into the next decade. Think of it as the steady widening of a lens. Early glimpses, then a flood. And what concretely will we do with these tiles? We will measure shapes, obsessively and fairly, correcting every optical quirk of the telescope, every drift of focus, and every imprint of the detector. We will estimate distances from colors with photometric redshifts and anchor them with the slitless spectra, so each faint oval on the sky is placed in its true shell in cosmic time. Then, we will stack statistics, correlations of shapes with shapes to weigh the invisible scaffolding, correlations of positions with positions to trace the acoustic ruler, cross-correlations with the cosmic microwave background to stitch late-time structure to the earliest relic light. In that stitching, we will look for the fingerprints of dark energy. Is it a simple cosmological constant, a pressure intrinsic to space, or does it breathe and evolve like a field? And if the latter, does it nudge gravity itself away from Einstein's elegant formulae at the largest scales? The map is our experiment. Even this first quick release hints at the avalanche to come. Newsrooms call it a treasure trove. Researchers talk about hundreds of strong lenses, hundreds of thousands of well-resolved galaxies, and the prospect of over 1 billion measured shapes by the end of the mission. These are not superlatives for their own sake. The strength of weak lensing lies in numbers, and the clarity of acoustic measurements lies in area. Euclid's design embraces both. But before we let the mind leap to final parameters and new physics, I want to slow down and look carefully at the craft. A three-dimensional atlas begins with a single tile. A single tile begins with a single shape. And a single shape must be measured against a point spread function that is known better than our own instincts. So let me take you into the discipline of measuring a galaxy's shape, when the distortion you seek is smaller than 1%, the quiet heart of weak lensing, and show you how we turn faint ovals into a weighing scale for the cosmos. I said the heart of weak lensing is a whisper of distortion, less than a single percent, so small that a telescope's own fingerprint can drown it out. That fingerprint is the point spread function, the way a perfect point of light, like a distant star, is blurred by optics, by the spacecraft's pointing, and by the detector itself. If you want to weigh the invisible scaffolding of dark matter from the tiny coherent stretch of background galaxies, you must know that fingerprint everywhere, every time, and you must subtract it with a delicacy that would make a watchmaker pause. Euclid's visible light camera, the visible instrument, was built for that discipline, a single, very broad optical filter to avoid color-dependent surprises. A tiled focal plane of charge-coupled devices arranged 6 by 6 and sampling tuned to capture the blurring in fine detail with a characteristic angular resolution of a few tenths of an arcsecond. That is the instrument's character. Uniformity over cleverness, stability over flourish. Shape measurement begins with humility. You do not trust a single galaxy. You trust 100,000, then 100 million. You do not trust an algorithm on its own. You teach it with images that you have simulated to look exactly like the sky you will see. The Euclid teams prepare galaxy image simulations not as a courtesy, but as a necessity, because even minute biases in shape estimation, additive leaks from the point spread function, or multiplicative errors that scale the shear itself can masquerade as cosmology. The literature names and tames those biases. It shows how detector quirks, subtle point spread variations, and imperfect methods produce exactly the spurious signals that a hurried analysis would claim as new physics. The cure is calibration, anchored in end-to-end simulations that include every nuisance you can think of, and a few you would rather not. So there is a rhythm to Euclid's craft. You build forward model skies. You draw galaxies with realistic structures and place them into the instrument's optical world. You convolve with the measured point spread function and add noise that behaves like the detectors. Then you run the very same shape measurement pipelines that will digest the real sky, and you measure the gap between the truth you planted and the answer you recovered. The gap becomes a calibration. A recent Euclid study asks how to shrink the computational burden of these calibrations, how to cancel noise efficiently and measure shear bias with fewer simulated images while still meeting the unforgiving precision demanded by Stage 4 lensing surveys. The answer involves clever pairings, response methods, and a relentless tally of uncertainties, because the mission can only tell us about dark energy if the systematics are beaten down to the level of a few parts in 1,000. Even realism has to be audited. Real galaxies are not tidy ellipses. They are knotty, clumpy, with star-forming regions and bars and tidal scars. If your simulations forget that complexity, the very messiness of nature leaks into your measurement as a quiet, cumulative bias. Euclid teams have begun to manufacture true galaxy morphologies by learning directly from deep Hubble Space Telescope images, using modern machine learning to generate ensembles of galaxies whose small-scale texture matches the sky itself, and then testing how that texture perturbs the recovered shear. This is not ornamentation. It is a way to respect the data, to ensure that the calibration actually spans the same universe of shapes that Euclid will observe. And then there is the crowding of the sky. At Euclid's depth, apparent neighbors often overlap. The light of a bright galaxy can hide a faint one, and a faint one just below the detection threshold can still bias the measured shape of the detected neighbor. That sounds like a nit, until you realize how the arithmetic of millions magnifies nits into genuine error budgets. The collaboration has mapped out how undetected galaxies and blending tilt the shear, and how joint analyses with deeper, sharper images or with complementary surveys can control that tilt. It is another reminder that weak lensing is as much about honesty with your instruments and data as it is about gravity. If the visible instrument supplies the shapes, the near-infrared spectrometer and photometer supplies the depth. With 3 broad near-infrared filters often named Y, J, and H, and slitless spectroscopy delivered by GRISMs, Euclid measures colors and redshifts for vast numbers of galaxies. The colors pin down photometric distances. The spectra, even at modest resolving power, anchor the whole ladder. In combination, they turn a flat mosaic into a 3-dimensional atlas, letting us sort galaxies into tomographic shells and watch the growth of structure unfold over cosmic time. In the instrument papers, you can feel the care, the pixel scales, the shared field of view, the way imaging and spectroscopy interlock so that weak lensing and galaxy clustering can be read from the same sky in the same way. The first quick data release is already a classroom for this method. It is not a cosmology fit. It is a rehearsal that contains real treasure. The catalogs include tens of millions of detections with visible light shapes, near-infrared photometry, and slitless spectra where available. From this material, teams have begun to assemble morphological atlases of hundreds of thousands of galaxies and to sift out hundreds of strong gravitational lenses, rare, precise rings and arcs that dramatize the very curvature of space-time. A Reuters report captured the scale in an ordinary register. 3 patches of sky, an area more than 300 moons across, some 26 million galaxies to a look-back time of over 10 billion years, and hundreds of lens candidates to sharpen our mass measurements. The poetry, if you like, hides in the statistics. There is something quietly radical here. For decades, our greatest space observatories have traded breadth for depth, exquisite, narrow fields that reveal the intimate life of galaxies. Euclid inverts the bargain. Within a month of beginning its survey, it had already surpassed the total area imaged by Hubble across more than 30 years, not because it sees everything more sharply, but because it sees enough uniformly at a scale that turns the sky itself into a laboratory. The data release calendar set by the mission, This first quick release, another next year, then the first full data release to follow, signals a cadence that the community can march to, building analyses that grow in area, in depth, in confidence, step by step. And yet all of that craft, the optics, the detectors, the simulations, the calibrations exists for a single question. How fast did the cosmic web grow, and what pushed or pulled upon it? To answer that, we must pair the shapes with distances, lay the slices of the universe in order, and then let the statistics speak. That is where the survey becomes a volume, and the tiles become threads in a three-dimensional web, which is exactly where I want to go next. Because once we have distances, we can watch gravity compete with the repulsive pressure we call dark energy, and we can ask, gently but firmly, whether Einstein's beautiful equation needs a footnote. So, once we have shapes, we need distances. A sky of elegant ovals becomes a volume only when each faint smear is placed into its proper shell in time. That is what Euclid does by marrying a sharp, visible camera to a near-infrared spectrometer and photometer, colors to estimate photometric distances for billions, spectra to anchor them for tens of millions. So, the panorama turns into a three-dimensional atlas of growth. In that atlas, we can watch gravity weave structure, while the strange pressure we call dark energy tugs the fabric outward, and ask which influence prevailed, and when. Photometric redshifts are the gentle workhorse of this transformation. You take the light of a galaxy in several broad bands, and by its hues, infer how far the cosmic expansion has stretched its spectrum and educated color to distance translation. For Euclid's weak lensing tomography, the requirement is unforgiving. The average redshift of each slice must be known to within roughly 2/1000ths, times 1 plus the slice's redshift, 0.00, 2 times, parenthesis, 1 plus z, parenthesis, so that a bias in distance does not masquerade as new. Physics in the sheer. Meeting that standard is not left to faith. The collaboration has built a calibration program around clustering redshifts, cross-correlating Euclid's photometric galaxies with spectroscopic samples so that shared structure reveals the true redshift distribution in each bin. It is a simple, beautiful idea. If two populations trace the same cosmic web on the sky, they overlap in distance. The measurement becomes a ruler for our colors. Alongside the colors sits a quieter anchor, slitless spectroscopy from Euclid's near-infrared instrument. A set of low-resolution grisms disperses the light of every source in the field, turning a single exposure into thousands of miniature spectra. The survey's spectroscopic heart is a bright line from hydrogen astronomers, call it H-alpha, which slides into Euclid's bandpass for redshifts from about 0.9 to about 1.8. Measuring that line for vast numbers of emission line galaxies gives exquisitely precise distances, targeting an accuracy of about 1 part in 1,000 in redshift, exactly what the standard ruler experiment of galaxy clustering demands. The instrument and mission design were tuned for this. Grisms with resolving power of a few hundred, a passband that catches the line across the desired era, and a survey strategy that repeats observations at different orientations to disentangle overlapping spectra. The method comes with its own puzzles. A single bright feature can be misidentified. An oxygen line can masquerade as hydrogen. Spectra can overlap. Noise can play tricks. Euclid addresses this with layered defenses. Dual grism angles to separate overlaps. Deep fields to characterize selection and error distributions. Photometric pre-selection to reject likely interlopers. And cross-checks against external spectroscopy. The preparation papers are frank about the risks and the cures. Interloper control, careful selection of emission line targets, and the use of deeper spectroscopic samples to map out the tails of the error distribution. In the first quick release, comparisons between Euclid's spectra and high-resolution ground measurements already show redshift dispersions down at the realm of a few times 10 to the minus 4 when hydrogen is present, an early, practical sign that the standard ruler ladder can be built with care. None of this lives in isolation. Euclid's philosophy is to let independent strands braid into strength. The colors come not only from Euclid's near-infrared bands, but from partner imaging on the ground. The spectra are cross-referenced with premier surveys that measure redshifts the old-fashioned way, line by line at high resolution. And the clustering redshift calibration is rehearsed on sophisticated simulations that embed galaxies in a realistic web. The partnership with next-generation imaging, what the Rubin Observatory will deliver from the southern sky, and with spectroscopic behemoths like the Dark Energy Spectroscopic Instrument, gives the calibration a backbone, turning the requirement, those 0.002 times parenthesis 1 plus z parenthesis targets, into a practical standard the community can meet. The quick release, the first true Euclid tiles, is already a classroom for this craft. 60 plus square degrees in the deep fields, tens of millions of sources, visible light shapes, near-infrared colors, and slitless spectra where the lines are kind, maps of the field geometry, and papers that use this material to demonstrate on real sky the pipelines that will soon digest a third of the heavens. You can see the cartographer's grid: Euclid Deep Field North, Euclid Deep Field South, and the Fornax region, each laid out as a lattice of pointings that will be revisited again and again until the word deep is earned in full. The language in the release is modest, the images are not. They already show the layered density of the web and the practical richness of the data that will set our distance ladder. With distances in hand, the volume of the universe resolves into slices, tomographic shells, each a thin time layer where we can measure two kinds of pattern. In the shapes, we find the subtle, coherent stretch that weighs the invisible scaffolding. In the positions, we find a faint ripple, a preferred separation imprinted in the primeval plasma, and left behind as galaxies formed, the baryon acoustic oscillation. The first pattern is a scale-free whisper of gravity, the second is a standard ruler. Pair them and you have an experiment that watches the geometry and the growth of the cosmos at once, pinning down how quickly space expands and how rapidly structure forms. Where they agree, confidence grows. Where they quarrel, new physics may be whispering. Euclid was built for that joint reading. And because this is a map made patiently, tile by tile, we will do it with a steady cadence, first small areas, then great swathes, first previews, then full releases, each wave better calibrated than the last, each cross-check more decisive. In the background sits a simple promise. A survey begun in mid-February 2024, a first public trove in mid-March 2025, future releases flowing outward until the atlas covers a third of the sky. It is cartography as a scientific method: return, refine, repeat, and let the universe reveal its pattern. And that brings us to the ruler itself, the quiet ripple in the galaxy distribution. Because once you accept that space carries a memory of ancient sound, you can use that memory to measure how the expansion has changed. So let me take you to that fossil wave and show you how a preferred separation becomes a clock and a yardstick at the same time. When I say a fossil wave, I mean an imprint from the time when the young universe was a hot, ringing fluid of light and matter. Pressure waves rolled through that plasma. When atoms first formed and light decoupled, those waves froze in place. Their last outward push left a preferred separation roughly 150 megaparsecs in co-moving distance, subtly encoded in where galaxies tend to be, not as a bright ring in the sky, but as a faint, statistical bump in their separations. That is the baryon acoustic oscillation, a standard ruler, and Euclid was designed to measure it across cosmic time so that the expansion history can be read directly from the geometry of the galaxy web. A ruler is only useful if you can lay it down in depth. That is why Euclid pairs its sharp, visible imaging with near-infrared colors and slitless spectra. Colors to estimate photometric distances for vast numbers of galaxies, and spectra to anchor those distances for tens of millions. The near-infrared spectrometer disperses every source in the field with low-resolution grisms, catching the bright hydrogen alpha line for galaxies from about 0.9 to about 1.8 in redshift. The very epoch when cosmic acceleration began to dominate, and it was built to do this uniformly across huge swathes of sky. Slitless spectroscopy is both elegant and tricky. With no slit to isolate each galaxy, spectra can overlap like notes in a crowded chord. Euclid's answer is strategy. Multiple grisms spanning blue and red wavelength ranges, observations at different dispersion angles and spacecraft roles, and deep fields revisited again and again, so that genuine lines stand out, while overlaps shift and can be disentangled. That design choice, repeat, rotate, and recombine, lets the team suppress interlopers and recover reliable redshifts for the emission line galaxies that carry the ruler. Already, in the first quick data release, the spectroscopic pipeline has been exercised on real sky. In the Euclid Deep Field North, the team cross-checked Euclid redshifts against high-quality measurements from the Dark Energy Spectroscopic Instrument, finding very small biases and impressive precision when the hydrogen alpha line is present early, practical evidence that this ladder can be built on the scales the mission requires. These checks will only become stronger as additional deep field passes accumulate and the second quick release and first full release arrive on their planned cadence. But let me linger on the idea of a standard ruler, because its beauty is in how simply it connects the story of the early universe to the late one. If you know the true length of that frozen sound wave, then whenever you see its echo in the clustering of galaxies, the apparent size tells you about distance. Measure the apparent size across the line of sight, and you read the angular diameter distance, measure it along the line of sight, and you read the Hubble expansion rate at that epoch. That twin measurement, the transverse and the radial, turns a fossil into a clock and a yardstick at once. Euclid's spectroscopic survey was conceived with exactly this in mind: to trace that ruler from roughly half the age of the universe to the present, and to do so over an area measured in tens of hundreds of square degrees, so that statistical noise gives way to clarity. The quick release gives us a rehearsal of the full performance. 3 deep fields north, south, and fornax, comprising just over 63 square degrees, already contain on the order of tens of millions of sources, with visible shapes, near-infrared colors, and slitless spectra wherever the lines are kind. They are only the first tiles in a mosaic that will eventually span about 1/3 of the sky. But even these previews map knots and filaments in satisfying detail, and seed catalogues of strong gravitational lenses and galaxy morphologies by the hundreds of thousands. For a cartographer, they are the first true pages of the atlas. There is another layer to the ruler's power. Gravity not only sets where the fossil bump appears, it also sculpts how galaxies stream toward clusters and along filaments. Those coherent motions leave a telltale squashing and stretching in redshift space distortions, which are sensitive to the rate at which structure grows. Combine the acoustic ruler with those streaming patterns, and you measure both the geometry of the universe and the tempo of gravitational growth. That pairing is where the deeper questions live. If dark energy is simply a constant pressure, Einstein's gravity should predict a very specific relationship between expansion and growth. If the data prefer a different relationship, the equations may be missing a footnote at the largest scales. Euclid's design weak lensing for mass, clustering for the ruler, and the flows, was tuned to make that comparison clean. Of course, the ruler must be protected from subtle biases. Galaxies are biased traces of the underlying matter. Non-linear clustering blurs the acoustic feature, and misidentified lines can sprinkle distant imposters into a given shell. These are not afterthoughts, they are part of the experiment. Euclid's approach is to fold them into end-to-end simulations and to use deep field repeats, multiple dispersion angles, and external spectroscopic anchors to model and subtract their influence until what remains is the cosmology. It is the same ethic that governs Euclid's weak lensing craft. Learn your instrument, simulate your sky, and let no bias go uncalibrated. Stand back from the technique and look at the arc. As of mid-March in the year 2025, Euclid had released this first trove, a trio of deep fields that together span just over 63 square degrees and hold something like 26 million galaxies, with future releases scheduled. Another quick release in late June of the year 2026, a first comprehensive release in late October of that same year, and a survey that, even by that date, had already imaged roughly 2,000 square degrees on the way to about 14,000. The cadence matters because cosmology is a discipline of accumulation. The statistics bloom as the atlas grows. So when I say we will lay down a ruler, I mean that quite literally. We will cross-correlate galaxy positions until the faint preference for that ancient separation emerges. We will fit it across shells in distance, and we will watch how the expansion and the growth conspire or diverge. And because the same sky yields Euclid's weak lensing shapes, we can check the growth by two independent routes, the streaming of galaxies and the shearing of light, each with different systematics, each able to catch the other if it stumbles. That is where I want to go next, to the growth itself, to the redshift space distortions that let us weigh the cosmic tug-of-war in motion, and to the way lensing and clustering together turn a map into a measurement of gravity. If a map is to measure gravity, it must catch matter not only where it sits, but how it moves. That is the quiet genius of redshift space distortions. Galaxies do not simply ride the Hubble flow. They stream toward the densest knots and slide along filaments. Those coherent motions make galaxy patterns look slightly squashed across the sky and gently stretched along our line of sight. Read carefully that squashing and stretching is a speedometer for growth. In the clean linear regime, the observable condenses to a single powerful combination. The logarithmic growth rate, which we call f, multiplied by sigma 8, the present-day amplitude of matter fluctuations. You will often see it written as f times sigma 8, and it is measured directly from the anisotropy of galaxy clustering in redshift space. Over the past decade, compilations of these measurements have sometimes leaned a little low compared to the oldest cosmic map from the microwave background, which is precisely why an all-sky, uniform survey like Euclid matters. It will watch the growth rate across time with the same instrument and the same method, and in doing so, it can arbitrate whispers of tension with calm statistics. What then does Euclid add? First, scale. Even this first quick installment, 63 square degrees, spread across the Euclid deep fields in the north, in the south, and toward Fornax, already contains on the order of tens of millions of sources. By mid-March of the year 2025, the mission had observed about 2,000 square degrees on its way to roughly 14,000, about one-third of the entire sky. The released tiles preview how these volumes will be threaded, with galaxies placed at known distances, ready for the subtle geometry of redshift space distortions to emerge. It is not rhetoric to call it a treasure trove. It is a description of the statistics we can now marshal. Second, design. Euclid's near-infrared spectrometer disperses the light of every source using low-resolution grisms, turning a single exposure into thousands of miniature spectra. The survey's spectroscopic heart is a bright line from hydrogen, often called the H-alpha line, which slips into Euclid's red grism for redshifts between roughly 0.9 and 1.8, the very era when cosmic acceleration began to dominate. Multiple dispersion angles and repeated visits disentangle overlapping spectra in crowded fields, while the visible band imaging supplies shapes and precise positions. It is a system chosen for uniformity across immense area, because redshift space distortions and the acoustic ruler both blossom when the sky is wide. We have already seen a rehearsal on real sky. In the quick data release, the collaboration put the spectroscopic pipeline through its paces on the deep fields and cross-checked Euclid's redshifts against high-resolution ground measurements. As you would hope, when the hydrogen line is within the grism's bandpass, the dispersions are small, and the biases are modest evidence that the ladder needed for the clustering experiment can be built in practice, not just in forecast papers. The team is frank about caveats: misidentified lines outside the designed redshift range, overlapping spectra in crowded regions, the need for selection criteria that avoid interlopers. But this is precisely the point of a quick release: to show the hand, to invite the community to learn the data's character while the wider atlas accumulates. Third, a joint reading. Euclid was conceived to braid galaxy clustering with its redshift space distortions and acoustic ruler, together with weak gravitational lensing, the subtle, coherent shear of galaxy images by foreground mass. The two probes watch the same cosmic web through different sensors. Clustering hears the fossil sound wave and the present-day streaming of galaxies. Lensing weighs the invisible scaffolding directly through light's deflection. Combine them, and the degeneracies that plague each separately begin to fall away. Geometry and growth can be tested at once, which is exactly how you ask whether dark energy is a simple cosmological constant or a field that evolves, and whether Einstein's beautiful theory needs a small, respectful footnote on the largest scales. Forecasts have been plain about the payoff. With the wide, uniform spectroscopic map, Euclid aims to measure the growth rate combination F times sigma 8 to percent level precision across multiple slices in redshift, while pinning down the product of angular diameter distance and Hubble expansion along the line of sight to sub-percent accuracy via the acoustic scale. Some studies go further, showing that even structures like cosmic voids can add leverage to redshift space distortions, providing complementary constraints within the same survey volume. The theme is consistent. Breadth and uniformity are themselves a kind of depth when it comes to growth. It helps to anchor those ambitions in the very texture of the quick release. The Euclid Deep Field Lattice, North, South and Fornax, is not just an aesthetic mosaic, it is a calibration engine. Each field will be revisited tens of times over the nominal mission at different rolls and dispersion angles. That cadence lets the team map selection functions, test redshift recovery in the presence of spectral overlap, and refine the photometric distance estimates that turn a flat catalogue into tomographic shells. By the time the first full data release arrives in late October of the year 2026, after a second quick release in late June, the pipelines will have been seasoned by real sky, and the combined lensing clustering analyses will be ready to bloom over areas measured in thousands of square degrees. When you put the pieces together, you can glimpse the question Euclid is poised to answer with grace. Does the measured growth of structure, as read from galaxy streaming and from the shear of light, match the expansion history inferred from the acoustic ruler, all under the umbrella of general relativity with a cosmological constant? Or does the data prefer a different dance, perhaps a slightly different amplitude of clustering today, perhaps a growth rate that drifts, perhaps a hint that gravity's long-range law is subtly modified? These are not dramatic departures dressed up as inevitabilities. They are measured, quantitative tests, built on an atlas that treats the sky with the same instrument and the same discipline, tile after tile. And so our map graduates from picture to measurement, distances from colors and from spectra, shapes from the visible camera, anisotropies from redshift space, stitched together to watch the cosmic tug-of-war unfold. In the next step, I want to sit with the lensing half of that braid, the shapes themselves, and show how a billion measured ovals can be turned into a weighing scale for the invisible, how the point spread function is tamed and the shear is calibrated, and how Euclid's first tiles already whisper the mass of the web they portray, which is where the cartography becomes a kind of quiet weighing of the universe itself. I promise to sit with the lensing half of the braid, the quiet craft of turning faint ovals into a weighing scale for the cosmos. So let me begin with the instrument that makes it possible. Euclid's visible imager is a single broadband camera whose entire personality is uniformity. A 6x6 array of large charge-coupled devices, more than 600 million pixels in all, sampling the sky at roughly 1/10 of an arcsecond per pixel, and delivering an effective sharpness of about 0.18 arcseconds once the multiple exposures are interlaced. It surveys over half a square degree at a time, and it was designed deliberately to take the same kind of picture everywhere, so that tiny coherent distortions can be trusted when they add up by the million. Weak lensing lives and dies by the point spread function, the telescope's own fingerprint on the light. Every star is, in truth, a little ellipse sculpted by optics, pointing, and detectors. If you do not know that ellipse precisely, you will mistake the instrument's preference for the universes. That is why Euclid's requirements on point spread knowledge are startlingly tight, down at the realm of a few times 10 to the minus 5 in the root mean square of its ellipticity components, and why entire teams devote themselves to modeling the point spread field across the focal plane, visit by visit, using the stars as calibration beacons. It is fussy work, but it is the difference between superstition and a scale that weighs invisible mass. Honesty comes next. You do not trust a single galaxy, you trust 100 million. And you do not trust even a perfect algorithm unless you have taught it with skies that look exactly like the ones you will observe. For Euclid, that means end-to-end image simulations. You draw galaxies with realistic structure. You convolve them with the measured point spread function. You add detector noise that behaves like the real thing, and you run the very same pipelines you will use on the sky. Then you measure the gap between the truth you planted and the shear you recovered, and you fold that gap back as a calibration. Entire papers are about how to accelerate this calibration without losing honesty, because the mission's cosmology only sings if residual, multiplicative, and additive biases are beaten down to parts per thousand and better. The sky itself complicates the lesson in subtle ways. Many galaxies are too faint to be detected, yet their light still lurks beneath the surface, blending with their neighbors and very gently tugging the measured shapes. It sounds like a knit until you remember the arithmetic of millions. Euclid's preparation studies show that if you ignore those undetected companions, especially if you ignore the fact that even the faintest galaxies are clustered, the recovered shear drifts by a few parts in 10,000 to a few parts in 100, large enough to masquerade as new physics if left uncorrected. The cure is to include the faint population down to extremely low surface brightness, with realistic clustering in the calibration simulations. It is a humbling reminder that lensing is as much about the ecology of images as it is about gravity. Real galaxies are not tidy ellipses, they are knotty, bar-streaked, clumpy things. If your simulations forget that texture, the small-scale structure leaks into your measurement as a cumulative bias. Euclid's teams have begun to manufacture true morphologies by learning directly from Hubble Space Telescope images, using deep learning to generate ensembles of galaxies whose fine-grained light resembles the sky we actually see, and then testing how that realism perturbs the recovered shear. The point is not fashion, it is fidelity, because a calibration trained on smooth toys can never quite correct a measurement made on snarled reality. Even the method of measuring the shear has been reimagined for this survey. One approach, developed within the collaboration, forward models each galaxy rather than squeezing it into prefabricated moments or profiles. It samples the full posterior distribution for shape parameters, explicitly accounting for the point spread function and marginalizing over nuisances. The philosophy is straightforward. If the convolution by the optics is of the same order as the galaxy's size, model the convolution, not the galaxy alone. It is computationally heavy, but the reward is control exactly what a billion measured shapes demand. All of this instrument craft and algorithmic humility shows up very concretely in what Euclid has chosen to release first. The quick data release 60 plus square degrees across 3 deep fields does not pretend to present final cosmology. It is a rehearsal, but a rehearsal with treasure, calibrated single epoch images from the visible and near-infrared instruments, merged mosaics, 2-dimensional and 1-dimensional slitless spectra, detection catalogs tied to the visible images, and even masks and maps of the point spread function across the fields. It is the raw material from which you can test shape pipelines on real stars and galaxies, measure the instrument's quirks, and begin to assemble shear catalogs that will become tomographic mass maps. You can feel the scale in the numbers. 3 fields, north, south, and fornax together, cover roughly 63 square degrees, on the order of 300 moons across the sky, and hold something like 26 million detected sources in this first pass alone. By the day of release, the mission as a whole had already imaged about 2,000 square degrees, on its way to roughly 14,000, about 1/3 of the entire sky. So the rehearsal will soon become the performance. But even now, in these first tiles, the lensing craft is visible. Star fields that map the point spread function, galaxy ensembles that exercise the shape pipelines, strong lenses to cross-check mass models, and the first statistical hints of the shear that will eventually weigh the web. Underpinning all of it is the visible instrument itself, described in loving detail by its builders: the pixel scale, the broad single optical band, the field of view, the way repeated exposures recover sub-pixel information to sharpen the effective resolution, the insistence that the same configuration be used everywhere so that systematic quirks can be learned and removed. It is a camera built not to dazzle with a single breathtaking picture, but to make a billion fair measurements. That is why its specifications read like a craftsman's ledger, and why the point spread requirements are written in exponents instead of adjectives. Stand back and the ethic is clear. Learn your fingerprint, simulate your sky, include every faint neighbor you cannot see, measure the gap and correct it. Only then are you allowed to ask the grand question: how much mass lies between us and those galaxies, and how does that mass grow with time? In the next step, I want to turn the crank on that question show how calibrated shapes become shear, how shear becomes a map, and how a map becomes a measurement of growth that we can set beside the fossil ruler in the galaxy distribution, because it is in that comparison geometry against growth that dark energy begins to come into focus. I said we would turn the crank, calibrated shapes into shear, shear into maps, and maps into growth. The first turn is translation. A galaxy's light has been blurred by the telescope's optics and pointing, and by the detector, the point spread function, and tilted by gravity on its journey to us. From each carefully modeled star field, we learn the instrument's fingerprint for that visit. From each faint oval, we then infer the residual, coherent stretch left by gravity. That inferred stretch is the shear. It is never trusted one by one. It is read statistically across tens of millions of galaxies, and its reliability rests on the uniform discipline of Euclid's visible instrument and its point spread modeling requirements that the mission spelled out long before launch and is now implementing on real sky. Once you have shears, you can make a picture of the invisible. There is a standard, beautiful inversion that turns a field of shears into a convergence map, the projected mass along the line of sight. In practice, Euclid will do this tomographically, in thin slices in distance, because the near-infrared colors and slitless spectra provide redshifts for vast numbers of galaxies. Stack the slices, and you begin to see the three-dimensional relief. Knots where clusters sit, filaments where matter streams, voids where it thins. Even in the first quick data release, just over 63 square degrees across 3 deep fields, the tiles already carry the material for such reconstructions. Calibrated visible images for shapes, near-infrared images, and spectra for distances, and the mass and maps that let one test the whole pipeline on real stars and galaxies. But lensing is a discipline of honesty. Before we trust a map, we try to break it. We decompose the shear field into 2 modes: the E mode, which gravity should produce, and the B mode, which gravity should not. Any significant B mode is a flare in the instrument room, a sign of leakage from the point spread function, blending, or calibration error. The Euclid preparation papers show this ethic in print: end-to-end simulations, noise cancellation tricks to measure tiny biases, and requirements on residual ellipticity errors driven down toward the realm of a few parts in 100,000, because that is what a billion honest measurements demand. There is another kind of honesty: cross-checking maps against statistics. Rather than making a picture, you can ask how the shear of galaxy pairs is correlated as a function of separation. Those 2 simple functions, the plus and minus correlations, are then transformed into band powers of the shear power spectrum in each tomographic shell. It sounds technical, but the payoff is clear. The power spectra respond to 2 things at once: the geometry of space, which sets how distances project, and the growth of structure, which sets how strong the mass fluctuations are. Lay those spectra beside the standard ruler in the galaxy, positions the baryon acoustic oscillation, and you have a paired reading of the late-time universe, geometry against growth. Euclid was designed for precisely this braid. Same sky, same selection, shapes and positions together. In the quick release, we are not yet publishing cosmology, we are rehearsing it with real data. The collaboration's overview is explicit. Q1 contains roughly 26 million detections across Euclid Deep Field North, Euclid Deep Field South, and the Fornax region. Calibrated, visible, and near-infrared images, slitless spectra for the brighter emission line sources, and the field masks, coverage maps, and point spread products needed to practice on the authentic sky. It is a classroom in which the community can begin to build shear catalogs, validate the B-mode null tests, and try the first mass reconstructions while the wider atlas accumulates. You can feel the scale from outside voices too. On the day of release, reports captured its simple facts: 3 sky patches, an area more than 300 moons across, some 26 million galaxies, out to more than 10 billion light-years, about 500 strong lensing candidates, and the promise that the next public wave will be vastly larger. Those are not superlatives for their own sake. They are the statistics that make a shear map robust, because weak lensing grows strong only in numbers. The instrument papers explain why Euclid can do this uniformly. The visible camera's pixel scale is tuned to sample the point spread function finely. Repeated subpixel dithers sharpen the effective resolution to around 0.18 arc seconds. And the same single broad optical band is used everywhere to avoid color-dependent surprises. Uniformity is not an aesthetic, it is a calibration strategy. When every field is taken the same way, the point spread fingerprint can be learned and removed in the same language across the entire atlas. Depth is the second half of the craft. With 3 near-infrared bands and slitless spectroscopy, Euclid places galaxies into distant shells, where the spectra catch the bright hydrogen alpha line, roughly from redshift 0.9 to about 1.8. The distances are exceptionally precise. Elsewhere, photometric estimates are anchored by clustering redshift techniques and by stacked spectral information, folding in external imaging as needed. The goal for lensing tomography is unforgiving. The average redshift of each bin to within about 2,000ths times 1 plus redshift. Yet this is precisely the calibration program that Euclid and its partners have planned. With shapes and distances in hand, the map begins to weigh. Mass reconstructions in each shell can be cross-correlated with galaxy density maps from the same tiles, with hot gas tracers in clusters, and with the lensing of the cosmic microwave background from other observatories. Each cross-check adds confidence, and each mismatch would be a clue. In the first deep field previews, hundreds of thousands of well-resolved galaxies and hundreds of strong lens candidates already hint at the structures these cross-correlations will probe. While the release cadence, this quick trove now, a larger one to come, then the first comprehensive release afterward sets the tempo for turning rehearsals into measurements. Stand back, and the logic is simple. Translate shapes into shear with ruthless calibration. Test for spurious modes until you are bored of finding none. Project shears into mass maps in distant slices. Then compress the maps into spectra that read geometry and growth together, and set those spectra beside the galaxy position ruler. Where they agree, the case for a simple constant dark energy pressure strengthens. Where they differ, the universe asks for a better story. And because the same tiles carry both senses lensing and clustering, the comparison will be clean. Which is exactly where I want to go next, to the joint fit itself, to the way a standard ruler and a shear spectrum braided over thousands of square degrees can sharpen the properties of dark energy and even test whether gravity's long-range law needs the gentlest of amendments. So now that the ruler in the galaxy positions and the shear in the galaxy shapes sit side by side on the same tiles, the question becomes, how do we braid them into a single measurement of the universe's geometry and growth? The practical answer is a joint fit. From clustering, we read the fossil wave, the preferred separation, imprinted when the young cosmos rang like a bell. And from redshift space distortions, we read how galaxies stream toward knots and along filaments. From weak lensing, we weigh the invisible scaffolding directly by the quiet, coherent stretch it paints on millions of faint ovals. Together, they test one simple proposition, that a constant, uniform pressure, what we call a cosmological constant, accounts for the late-time acceleration, and that Einstein's gravity needs no amendment on the largest scales. Euclid was conceived explicitly to ask that question with calm statistics, because all three signals are gathered uniformly by the same instruments across an atlas that will eventually span roughly 1/3 of the sky. The braid works because each probe carries different degeneracies. The acoustic ruler fixes distance ratios. The streaming of galaxies fixes a particular combination of the growth rate and the present-day clumpiness, the quantity astronomers abbreviate as F times sigma 8, and the lensing spectra fix the amplitude of matter fluctuations in projection, insensitive to how galaxies choose to occupy halos. Bring them together, and parameters that wander when measured alone snap into focus. Forecast studies done before launch, and refined since, show precisely this complementarity. With Euclid quality area and depth, the growth rate combination can be mapped in redshift slices with percent-level precision, while the acoustic yardstick can fix angular diameter distances and the Hubble expansion along the line of sight to sub-percent in the clean linear regime. Add lensing, and the joint constraints on the dark energy equation of state parameters, often written as W0 and WA sharpened dramatically, in some cases rivaling combinations that once required multiple, disparate surveys. All of that promise now has a tangible stage. On the 19th of March, in the year 2025, Euclid released its first quick set of survey tiles. 3 deep field regions, north, south, and 4 NACs covering just over 63 square degrees and containing something like 26 million detected sources, with visible band shapes, near-infrared colors, and slitless spectra, where the lines are kind. As the European Space Agency put it that day, this was a treasure trove, a preview of the larger atlas to come. Journalists reached for ordinary metaphors, hundreds of moons of sky, billions of years in depth, to capture the scale. By release day, the mission had already imaged on the order of 2,000 square degrees, on the way to roughly 14,000. And the schedule set a clear cadence. This first trove now, a larger public wave to follow, and the first comprehensive release planned for late October of the year 2026. If you want to feel how the joint fit will be done, you can already see the pieces in the instrument papers. The visible camera, a 6x6 mosaic of large charge-coupled devices, sampling the sky at roughly 1/10 of an arc-second per pixel, records shapes in a single broad optical band so that color-dependent surprises do not leak into the shear. Repeated sub-pixel dithers recover an effective sharpness of about 0.18 arc-seconds, fine enough to read the tiny coherent stretching that weak lensing demands. The near-infrared spectrometer and photometer covers the same field of view, delivering 3 near-infrared bands for color distances and slitless spectra that catch the bright hydrogen alpha line for galaxies from roughly redshift 0.9 to about 1.8, exactly the era where the acoustic yardstick and the streaming patterns bloom. A joint analysis is also a joint discipline. The photometric distances that enable lensing tomography must be calibrated at the level of a few parts in 1,000 in the bin averages, typically by clustering redshifts, cross-correlating Euclid's photometric samples with spectroscopic anchors so that shared structure reveals the true distribution. The slitless spectra, elegant and prolific, come with their own craft, multiple dispersion angles and repeated visits to disentangle overlaps, photometric pre-selection to suppress imposters, and deep field passes to learn the tails of the error distribution. The first quick release papers are frank about these details and, just as importantly, show early cross-checks against high-resolution ground spectroscopy that place the expected precision within reach when the hydrogen line is present. This is the rehearsal you want before the atlas grows by orders of magnitude. What will the braid tell us once the survey's wide swathes arrive? At a minimum, it will test whether distances traced by the acoustic ruler and growth traced by lensing and streaming agree within Einstein's framework when dark energy is a constant. If they do, the dark energy pressure will look ever more like a property of space itself, and the famous parameters W0 and WA will settle toward -1 and 0 with smaller and smaller error bars. If they diverge, if, for instance, the growth comes in persistently low compared to the geometry, the case for evolution in the dark energy sector, or for a gentle amendment to gravity's long-range law, will strengthen. Forecasts within the Euclid program even show that adding cosmic voids, the great underdensities that pockmark the web, can improve redshift space, distortion measurements and distance ratios via the Alcott-Paczynski effect, further tightening the joint net. It is the old lesson of cartography. Breadth and uniformity are a kind of depth. And because the same sky is seen by both instruments, Euclid can form still richer combinations. The shear maps can be cross-correlated with the galaxy density maps from the spectroscopic sample to break galaxy bias degeneracies. They can also be paired with lensing of the cosmic microwave background from other observatories, tying late-time structure to the earliest fossil light. Each cross-check is both a measurement and a test for spurious modes, a way to insist that the picture is earned rather than assumed. In that sense, this first quick-release calibrated images, spectra, masks, and early catalogs does exactly what it should. It invites the community to exercise the full joint pipeline on real sky, while the survey quietly spreads. Stand back, and you can see where the story is going. The atlas will grow tile by tile. The ruler and the shear will be read slice by slice. The fits will land first as rehearsals, and then as measurements, pressing down on the space of possibilities, until the dark energy story either simplifies beautifully or asks for a new chapter. Before we step into that parameter space, the plane of W0 and WA, and the simple growth index that lets us test gravity directly, I want to show you one more piece of the craft that makes the joint fit honest. How Euclid turns a sky of exquisite pictures into uniform, fair statistics, and how a billion measurements across a third of the heavens are taught to speak with one voice. When I say we teach a billion measurements to speak with one voice, I mean we turn pictures into statistics that are fair, uniform across the sky, immune to local quirks, and honest about what they do not know. Euclid was built for that kind of fairness. The visible imager, a 6x6 mosaic of charge-coupled devices sampling the sky at roughly 1/10 of an arcsecond per pixel, always shoots through the same single, very broad optical filter. Repeated subpixel dithers recover an effective sharpness of about 0.18 arcseconds. It is the photographic equivalent of a metronome, the same beat everywhere, so that tiny coherent stretches in galaxy shapes can be trusted when we add them up by the 100 million. Uniform pictures are necessary, but not sufficient. The pipeline must be equally uniform. That is why the processing functions for the two instruments, the visible camera and the near-infrared spectrometer and photometer, were written as reference recipes and stress-tested on orbit. The visible processing function describes, step by step, how raw frames become calibrated images with controlled image quality, astrometric accuracy, and photometric 0 points. The near-infrared processing function does the same for both imaging and slitless spectra, removing instrumental signatures, aligning the astrometry, setting the photometry, and then stacking. The first quick tiles, real sky, over more than 63 square degrees, demonstrate that these metrics sit within the pre-launch specifications. That is the quiet foundation beneath every map you will see. Then come the products that make statistics possible. Euclid's first quick data release is not a cosmology fit. It is a classroom with all the chalk on the board. Calibrated single epoch frames from both instruments, merged mosaics, one-dimensional co-added spectra, spectroscopic redshift catalogs, and, crucially, the masks and maps coverage maps, root mean square noise maps, and point spread function maps that let us weight each patch of the sky for what it truly is. Add the external ground-based imaging in the traditional optical bands, and you have the color information needed to place galaxies into distant slices ready for lensing tomography. This is how beautiful pictures become fair numbers. Fairness begins at the telescope, but it is enforced in the survey's choreography. Euclid steps across the heavens in a step and stare rhythm, with carefully designed dithers that fill chip gaps, sample the point spread function, and average over pixel-level quirks. The reference survey was engineered to minimize attitude changes as it walks from tile to tile. No flourish, just steadiness, because thermal stability and repeatable optics are a currency in weak lensing. Deep fields at the ecliptic poles and toward the Fornax constellation are revisited again and again at different roll angles. Those repeats teach us selection functions, disentangle overlapping slitless spectra, and season the pipelines on real sky before the wide atlas floods in. Even the numbers in the headlines are parts of this fairness. The first quick release covers roughly 63.1 square degrees, with on the order of 26 to 30 million detections spread across three regions: the Euclid Deep Field North, the Euclid Deep Field South, and the Fornax region, each observed to the nominal depth of the wide survey. It is only the first lattice in an atlas that will, over the nominal mission, grow to about 14,000 square degrees of extragalactic sky. The quick release is staged as a rehearsal, a place to test, calibrate, and learn before the first comprehensive data wave arrives. But a fair atlas also needs fair distances. For the lensing tomography, the mean redshift of each slice must be known to within about 2,000ths, times parenthesis 1 plus redshift parenthesis, an unforgiving target. Euclid's plan is pragmatic. First, near-infrared colors measured from space are combined with ground-based optical colors to estimate photometric distances for vast numbers of galaxies. Second, those estimates are anchored statistically by clustering redshifts. You cross-correlate the photometric galaxies with spectroscopic samples, both Euclid's own slitless spectra, where the bright hydrogen alpha line appears, and external surveys to infer the true redshift distribution of each bin. Mock catalog studies on Euclid-like simulations now show that this method can meet the target precision when handled with care about galaxy bias and small-scale physics. On the spectroscopic side, uniformity is protected by design rather than by hope. The near-infrared spectrometer disperses the light of every source with low-resolution grisms. The survey is tuned to catch the hydrogen alpha line for galaxies between roughly redshift 0.9 and 1.8, the very era where the acoustic ruler and redshift space distortions are most powerful. Multiple dispersion angles and repeated passes at different spacecraft roles let overlapping spectra slide apart in the data reduction, reducing imposters and stabilizing the selection. In short, repeat, rotate, and recombine until the catalog behaves like a uniform instrument. Uniformity also means we acknowledge, quantify, and publish our warts. The quick release includes masks that flag the edges of coverage, bright star halos, detector artifacts, and depth variations. It includes maps of the point spread function so that the instrument's fingerprint can be modeled rather than guessed. That transparency is not decoration. Weak lensing grows strong only in numbers, and biases as small as a few parts in 1,000 matter. Publishing the masks is how we allow the community to wait and test the data honestly, and how independent analyses can converge rather than diverge. Behind the scenes, a second ethic protects the statistics. We look for the wrong answer on purpose. In shear maps, we split the signal into two modes: the E mode, which gravity should produce, and the B mode, which gravity should not. Any significant B mode is a flare in the instrument room. In distance calibration, we cross-check photometric estimates against clustering redshift inferences and against Euclid's own slitless spectra where the line is present. In the pipelines themselves, on-orbit performance is compared with pre-launch simulations and requirements. When the numbers line up, image quality, astrometry, photometric calibration, we give ourselves permission to listen to the cosmology. All of this craft serves a simple arc. By the 19th of March in the year 2025, the survey had already delivered its first public tiles. Another quick release is calendared for late June of the year 2026. The first comprehensive data release follows in late October of the same year. Each wave widens the atlas and tightens the calibrations. Each wave feeds joint fits that braid the acoustic ruler, the streaming of galaxies, and the shear of light into one measurement of geometry and growth. That is the cadence by which a map becomes a verdict. And because a verdict wants parameters, I want to walk there next gently into the plane, where we write dark energy as an equation of state with two numbers, into the growth index that lets us test gravity directly, and into the way Euclid's uniform statistics will press those numbers down until the story either simplifies beautifully or asks for a new chapter. Now gently into the plane where dark energy is given a voice. When cosmologists talk about what the pressure of the dark component is doing, we usually paint it with two numbers. We call them W0 and WA. They belong to the Chevalier-Pulaski-Linde picture, in which the pressure-to-density ratio, the equation of state W, is written as W of A equals W0 plus WA times 1 minus A, where A is the cosmic scale factor. In plain words, W0 tells you the pressure today, WA tells you how it drifts with time. If dark energy is simply a cosmological constant, the story is unchanging. W0 equals -1 and WA equals 0. Anything else, anything that bends away from that calm point, whispers of fields or interactions, or a subtle tweak to gravity's long-range law. This two-number map is not the universe, but it is an honest, compact stage on which the data can speak. Beside that stage, we set a second ruler for gravity itself, the growth index, usually written as the Greek letter gamma. In Einstein's theory, folded together with ordinary cold dark matter and a cosmological constant, gamma sits very near 0.55. Push gravity around on the largest scales, and gamma is one of the places it will show. This is why Euclid was designed to read geometry and growth at once, to see where the distances traced by the acoustic ruler agree with the way structure actually gathers, and whether both agree with that quiet value of gamma. Everything I have described needs a map that is wide, uniform and deep, one set of eyes, one way of looking spread over a third of the entire sky. Even in this first quick release, Euclid has shown its way of working. 3 deep fields, one in the north, one in the south, and one toward the Fornax constellation, together amount to a little over 63 square degrees, more than 300 moons of area, with roughly 26 million galaxies already in hand from just a single sweep. By the day of release, in mid-March of the year 2025, the spacecraft had already imaged about 2,000 square degrees, on its way to about 14,000. The project set a rhythm, quick tiles now to tune our methods, a major cosmology data wave planned for late October 2026, and the deep fields visited tens of times to become truly deep. To read geometry, Euclid's near-infrared spectrometer and photometer, what we call the near-infrared spectrometer and photometer, abbreviated as NISP, disperses the light of every source with low-resolution grisms. Its sweet spot is the bright hydrogen alpha line, which falls into the red grism for redshifts roughly from 0.9 to 1.8, exactly the era when the late-time acceleration becomes most visible. The instrument's field of view matches the visible camera. 16 detectors, each 2,000 by 2,000 pixels, sample the sky at about 0.3 arc-seconds per pixel. The grism set includes 1 blue and 3 red dispersers, and the slitless spectra are taken at multiple angles to tease apart overlaps. That uniform design is what makes a clean acoustic ruler and clean redshift space distortions at vast scale possible. To read growth, Euclid's visible imager, the visible instrument, abbreviated as VIS, was built as a metronome. 6x6 large charge-coupled devices, 609 million pixels, a pixel scale of 1/10 of an arc-second, and an effective sharpness of about 0.18 arc-seconds, thanks to repeated sub-pixel dithers. It observes through one broad optical band everywhere, precisely to make the lensing shear a fair statistic across the sky. You can feel the intention in those numbers. Not a single pretty picture camera, but a billion fair measurements stitched into a single voice. What will these two instruments, together, do to those two dark energy numbers? Forecasts run before launch and updated since show the logic. With the wide spectroscopic map, Euclid measures the ruler written in the galaxy distribution and the gentle squashing and stretching we call redshift space distortions. Those distortions give a direct grasp of the growth rate combination, often spoken as F times sigma 8. With the lensing shear spectra from VIS, the mission weighs the projected mass fluctuations independent of how galaxies choose to occupy halos. Braid them, and the W0 and WA plane tightens. The growth index gamma, tested against the distances, becomes a way to ask, is gravity as simple as we think? And to quantify how, not if not. Forecast studies coupling Euclid to the cosmic microwave background go further, showing that the combined lever arm can sharpen parameter uncertainties by factors of a few, and sometimes an order of magnitude, compared to either alone. Even structures that once seemed like byproducts become tools in this joint fit. Euclid will map thousands upon thousands of cosmic voids, the great underdensities that pock the web, and the average shapes of those voids, squashed or stretched along our line of sight by the way we translate redshifts to distances, carry a clean geometric signature called the Alcock-Paczynski effect. Forecasts built on Euclid's flagship simulations suggest that a void analysis can reach relative precision at the level of a few percent on the growth-to-bias ratio and sub-percent on a specific product of distance and expansion in several slices of time numbers that complement the classical ruler and streaming fits, and that drops straight into the W0 and WA plane and into gamma. The first deep field release shows the stagecraft of this approach with pleasing clarity. The telescope presents 3 great swathes, 60 plus square degrees altogether, to be revisited between 30 and 52 times, and even now, after just one pass, it has gathered on the order of tens of millions of galaxies and hundreds of strong lensing candidates. Journalists wrote of an avalanche, and that is not hyperbole. For cosmology, though, the point of the avalanche is calm. It is the law of large numbers applied to the universe, turning tiny shears and subtle streaming into parameters you can put beside a cosmological constant and ask, does the story close? Underneath the promises, there is honest plumbing. The visible image's pixel scale, the field of view shared between visible and near infrared, the GRISM set, the spectral resolution near 400 for compact sources, all of these things are carefully documented because they feed directly into the joint likelihood that will soon fit distances and growth together. And Euclid's quick tiles were released not as a final verdict, but as a rehearsal with real sky, precisely so that pipelines could be tested against the hardware's true fingerprint while the atlas accumulates. So the plan is simple and beautiful. We walk the W0, WA plane with a ruler made of fossil sound and a scale made of shear. We test gamma, the growth index, as a fairness check on gravity itself. We do it on the same sky, with the same instruments, tile by tile, until the error bars sit small enough that the dark energy either behaves like a constant, politely, or asks for a better tail. In the next stretch, I want to lean closer to those parameters to show how the ruler appears as ripples in the clustering spectra, how the shear power speaks in its own vowels and consonants, and how the first Euclid tiles already let us practice the very compression that lands a point in the W0 WA plane and a band for gamma. Let me lean closer, as promised, to the way the data themselves speak, how the fossil wave shows up as gentle ripples in the clustering spectrum, how the whisper of shear becomes vowels and consonants in a power spectrum of shapes, and how even these first Euclid tiles let us rehearse the compression that lands a point in the W0 WA plane and a band for the growth index. The stage is real sky. 3 deep fields, just over 63.1 square degrees. Released on the 19th of March in the year 2025 as Euclid's first quick set of survey tiles. They are small beside the atlas to come, but they are large enough and clean enough to practice turning pictures into fair statistics. In the galaxy positions, the story is a rhythm. Imagine laying down pairs of galaxies and asking how often they are separated by a given distance. You get a correlation function that carries a faint bump at a special separation, the imprint of ancient sound. Take the same information into Fourier space, and the bump becomes a slow set of wiggles in the power spectrum. Either way, the ruler is present as a modest preference, not a ring in the sky, but a statistical echo. The first Euclid quictiles let us test the mechanics of measuring that echo on Euclid data products, calibrated mosaics, masks, and redshift estimates before the ocean of area arrives. That is their purpose, to show what is in hand and to let the community rehearse the analysis chain on a uniform, space-based dataset. In the shapes, the language is a different music. We do not look for peaks. We ask how the tiny, coherent stretch of galaxy images is correlated across angle and across distance. The answer is a tomographic shear power spectrum. For each pair of redshift slices, a function of angular scale that responds jointly to geometry and to growth. Its cleanest test is silence, where there should be silence. The so-called B mode, a parity partner to the signal that gravity should not produce in the linear regime. Euclid's first processing papers describe in sober detail how the visible camera frames are calibrated into images that meet their pre-launch promises. Precisely so, those 2-point measurements can be trusted when the atlas grows. And the requirement that makes tomography meaningful, that the mean redshift of each slice be known to within about 0.002 times parenthesis, 1 plus redshift parenthesis, is not a slogan but a target demonstrated in Euclid's calibration program and studies built for Euclid-like data. Of course, cosmology is never a single instrument or a single statistic. It is a braid. The shorthand within the field is 3 by 2 point, because we weave together 3 kinds of 2-point correlation: shear with shear, galaxies with galaxies, and galaxies with shear. The last of these galaxy-galaxy lensing ties, where matter sits to how light is bent, breaking degeneracies that each probe would carry alone. Forecasts built for Euclid show how this combination sharpens the story. Remove small-scale modeling where you must. Keep the clean linear regime where you can, and the joint likelihood still lands with formidable precision on the parameters that describe dark energy and growth. These are not abstractions, they are the analysis forms. Euclid was designed to deliver on a sky measured in tens of hundreds of square degrees. That is why we give dark energy a 2-number map. In the Chevalier-Pulaski-Linde picture, the equation of state is written as W of A equals W naught plus WA times parenthesis 1 minus A parenthesis, 1 number for the pressure today, 1 for how it drifts. If the dark component is simply a cosmological constant, W naught equals -1 and WA equals 0. Alongside sits a second diagnostic, the growth index gamma, which in Einstein's gravity, with cold dark matter and a cosmological constant, lives near 0.55. The beauty of Euclid's design is that distance and growth can be read from the same sky with different senses, so we can ask whether the point preferred by geometry is the same point preferred by growth. The instruments themselves explain why this works. The near-infrared spectrometer and photometer disperses every source with low-resolution grisms and was tuned to catch the bright hydrogen alpha line for galaxies from roughly redshift 0.9 to about 1.8, exactly the era where the acoustic ruler is clean and where streaming along filaments reads like a speedometer for growth. The visible imager measures shapes in a single, very broad optical band with a pixel scale of 1/10 of an arc second and an effective sharpness after subpixel dithers of about 0.18 arcseconds. Uniformity is the philosophy, the same way of looking everywhere, so that statistics can be fair when added across a third of the sky. Early practical rehearsals have already been done on real sky. In the quick release, the spectroscopic pipeline's redshifts were compared in the Euclid Deep Field North against high-quality ground measurements, and when hydrogen alpha is within the designed passband, the biases and dispersions come in small, an encouraging sign that the ladder for clustering and redshift space distortions can be built in practice, not just in forecasts. The technical papers that accompany QUONE also lay bare the limits. Overlaps in slitless spectra, interlopers outside the target redshift, selection that must be tuned. But that is the point of a rehearsal. We learn the warts while the larger atlas accumulates. And the atlas will be large. Euclid's wide survey is designed to cover about 14,000 square degrees of extragalactic sky, avoiding the crowded plane of our own galaxy, with deep fields interleaved for calibration and depth. The first public tiles simply set the cadence. Quick data in March 2025 to tune the pipelines. Another quick wave to follow, and the first comprehensive data release planned for late October 2026. The reason to emphasize cadence is simple. The precision grows with the map, and the map grows tile by tile. So, here is the quiet alchemy we will practice over and over. From the galaxy positions, we compress the correlation data into a measurement of the acoustic scale across and along the line of sight, reading distances, and the Hubble expansion at a given epoch. From the anisotropy of clustering, we read the growth rate combination often spoken as F times sigma 8. From the shapes, we build tomographic shear power spectra and their cross correlations with galaxy density, weighing mass directly. Then we fit all of it at once on the same sky, asking whether the point W0 equals -1, WA equals 0, with gamma near 0.55 is the point the universe prefers, or whether the data, politely but firmly, ask for drift, for a coupling, or for a gentle amendment to gravity's long-range law. That is the experiment Euclid was built to run. And because experiments are built not only on promise but on plumbing, in the next stretch I want to open the hood properly, to show how the compression is done in practice on Euclid products. The masks, the point spread maps, the one-dimensional spectra, how small-scale astrophysics is tamed rather than ignored, and how cross-checks with independent sky, from ground-based surveys to the oldest fossil light, steady the hand before we draw our first contours on the W0WA plane. Let me actually open the hood, as promised, and show how a Euclid tile becomes a number. You can trust how we compress calibrated pictures and spectra into clean, uniform statistics, and how we tame the messy, beautiful physics that lives on small scales, so it does not masquerade as new cosmology. First, the products. A single public tile does not arrive as a pretty postcard. It arrives with everything you need to treat it fairly. Calibrated single-epoch frames from the visible camera and from the near-infrared spectrometer and photometer, merged mosaics, one-dimensional co-added spectra for slitless observations, object catalogues, and, crucially, the masks and maps coverage, noise, and point spread function that let us weight each pixel for what it truly is. Euclid's first quick data release, on Wednesday the 19th of March in the year 2025, bundled those ingredients for 3 deep fields, covering about 63.1 square degrees and roughly 26 million detections. It is a rehearsal rather than a verdict, but it is a rehearsal with real sky and real plumbing. Under that plumbing sit, the 2 processing functions, the reference pipelines that turn raw frames into calibrated survey quality products. The visible processing function spells out, step by step, how point spread shape, astrometry, and photometric 0 points are brought within pre-launch promises on orbit. The near-infrared processing function does the equivalent for imaging and for slitless spectra. removing instrumental signatures, tying the astrometry, setting the photometry, and then stacking. Quone shows those functions working on real sky, with headline metrics, image quality, astrometric accuracy, photometric calibration comfortably within specification. That is the quiet foundation beneath every correlation function and power spectrum we will soon publish. Now to compression. On the galaxy position side, we lay down pairs of galaxies and ask how often they occur at a given separation, correcting for the mask and waiting by the noise maps you were given. In configuration space, the ancient acoustic ripple appears as a gentle bump. In Fourier space, as slow wiggles in the power spectrum. Either way, we use only scales that theory and calibration can support cleanly. Euclid's quick tiles are exactly for this, to practice the estimators and the scale cuts on a uniform, space-based dataset before the ocean of area arrives. On the lensing side, we translate shapes into shears, shear into tomographic convergence maps, and maps into two-point statistics. The shear field is decomposed into its parity partners, an E mode, which gravity should generate, and a B mode, which it should not, in the linear regime. The first test of honesty is silence, where silence should be a B mode consistent with 0. Once masks and weights are respected, you can feel why Euclid's visible camera was designed as a metronome here. A 6x6 charge-coupled device mosaic, about 609 million pixels, sampled at roughly 1/10 of an arcsecond per pixel, and an effective sharpness near 0.18 arcseconds. Once the dither pattern is interlaced, the same single broad optical band everywhere, precisely so that tiny coherent stretches can be trusted when they add up by the 100 million. Depth turns pictures into a volume. The near-infrared spectrometer and photometer disperses every source with low-resolution grisms. Its sweet spot is the bright hydrogen alpha line, which drops into the red grisms for redshifts from roughly 0.9 to about 1.8. The very era where the acoustic ruler is clean and galaxy streaming reads growth like a speedometer. Multiple dispersion angles and repeated field visits are baked into the survey to pry apart overlapping slitless spectra, while the imaging channels provide the colors needed for photometric distances. Those design choices are why the clustering and redshift space distortion experiments can be done uniformly across vast areas. Distances must be honest as well as deep. For weak lensing tomography to be cosmology rather than wishful thinking, the mean redshift of each slice must be known to within about 2,000th times, parenthesis 1 plus redshift parenthesis. Euclid does not leave that to faith. The plan, and now the practice, is to calibrate ensemble redshifts, statistically by clustering redshifts, cross-correlating Euclid's photometric galaxies with spectroscopic samples, including Euclid's own slitless detections, so that shared structure reveals each bin's true distribution. Recent Euclid studies, run on flagship quality simulations and realistic spectroscopic mocks, have demonstrated that this method can meet the 0.002 times parenthesis 1 plus z parenthesis target when galaxy bias and small scales are handled with care. Then there is the sky's delightful messiness, the part we love for galaxy evolution and must control for cosmology. Baryonic physics stirs the matter field on small scales. Feedback from stars and black holes, puffs and smooths. Modified gravity models can mimic some of those signatures. Euclid's answer is not to pretend otherwise, but to cut and to model. Impose conservative scale cuts where theory is least certain. Propagate supersample covariance from modes larger than the field. And use physically motivated halo model responses or calibrated emulators to account for baryons tested on hydrodynamic simulations. The preparation papers quantify exactly how those choices relax or sharpen the 3x2 point constraints, so you know what you have bought when you buy cleanliness. A second nuisance is intrinsic alignments. Galaxies can preferentially orient with their local tidal field even before lensing bends their light. Leave that unmodeled, and you would interpret a sociable galaxy's preference as extra gravity. Euclid treats it as a parametrized contaminant with an amplitude, and simple redshift and luminosity scalings marginalized over in the joint fit and checked against external data. That nuisance family sits explicitly in Euclid's Fisher forecasts and likelihoods, so it is measured and absorbed rather than hand-waved away. Compression, finally, is a braid, the 3x2 point combination. We measure galaxies with galaxies, shear with shear, and galaxies with shear. The last of those galaxy-galaxy lensing ties, where mass sits to how light is bent and helps break the bias degeneracy in clustering alone. We keep to linear and quasi-linear scales. Where the theory is cleanest, apply the scale cuts and baryon treatments you have seen, and feed the lot to a joint likelihood that returns distances, growth, and their covariances. The forecasts that shaped Euclid were written in that language, and the cross-checks do not end at Euclid's focal plane. The same tiles can be paired with lensing of the cosmic microwave background from other observatories to bridge late-time structure to the earliest fossil light. They can be cross-correlated with independent spectroscopic surveys to steady the redshift ladder, and they can be combined with the microwave background itself to tighten dark energy and curvature constraints. The leverage of that recombination to today's span was part of Euclid's plan from the beginning. When you see it all laid out, masks and point spread maps, one-dimensional spectra and color catalogs, scale cuts and nuisance families, you begin to appreciate the ethic. Publish the warts, measure the nuisances, and let only the clean parts of the sky speak for cosmology. Which brings us, at last, to the parameters themselves, how this compression lands a point in the plane of W0 and WA, and a band for the growth index, how the early, small tiles already let us rehearse that landing, and how the atlas, as it grows toward a third of the sky, will press those points down until the dark energy either behaves politely like a constant or asks us for a better story next. So this is where the rehearsal becomes a first, careful landing on the map, the place where pictures and spectra compress into a point in the plane of W0 and WA, and a band for the growth index we call gamma. The stage is modest on paper and vast in practice. 3 Euclid deep fields north, south, and fornax, adding up to a little over 63.1 square degrees. Released on Wednesday the 19th of March in the year 2025, with around 26 million detections and the full kit of calibrated images, slitless spectra, catalogs, and the masks you need to treat every pixel honestly. The collaboration is explicit. This is not a cosmology verdict. It is a quick release designed to let us sharpen tools on real sky while the atlas grows. That honesty is exactly what you want before drawing the first contours. In a joint fit, I like to imagine the data speaking different dialects of the same story. The visible imager, Euclid's metronome, with a 6x6 mosaic of charge-coupled devices at roughly 1/10 of an arcsecond per pixel, gives me shapes in one very broad optical band everywhere, so that a whisper of shear can be trusted when it is added up by the 100 million. The near-infrared spectrometer and photometer covers the same field, gives me 3 near-infrared colors for photometric distances, and disperses every source with low-resolution grisms to catch bright emission lines, most usefully the hydrogen alpha line, so that positions on the sky become distances along the line of sight. That is how a flat tapestry becomes a 3-dimensional atlas. Once those dialects are fluent, the compression itself is rather musical. From galaxy positions, we measure the slow wiggles of the fossil sound wave, the baryon acoustic oscillation, and because galaxies stream toward knots, we read a gentle squashing and stretching in redshift space. The redshift space distortions that give us the growth rate combination usually spoken as F times sigma 8. From shapes, we measure the tomographic shear power spectrum, the way coherent stretching correlates across angular scale and across distance. The three pieces together, clustering with clustering, shear with shear, and the cross-correlation of galaxies with shear make the 3x2 point braid that Euclid was built to deliver on a sky measured not in patches, but in swathes. You can feel why the redshift ladder matters so much. For shear tomography, to speak the language of cosmology rather than wishful thinking, the mean redshift of each tomographic slice must be known to within about 2,000th times, parenthesis, 1 plus redshift, parenthesis. That is not a slogan. It is a requirement Euclid has worked toward for years with clustering redshifts, cross-correlating the photometric sample with spectroscopic anchors, including Euclid's own slitless spectra in the hydrogen alpha suite. Spot to infer the true distribution of each bin. Fresh Euclid studies using flagship quality simulations now show in practical detail how to reach that unforgiving accuracy and where the pitfalls lie: galaxy bias, small-scale clustering, and the need to avoid separations where one halo physics confuses the ruler. The spectroscopic half of the braid has been designed like a surveyor's rod. Euclid's near-infrared spectrometer and photometer uses a set of low-resolution grisms resolving powers in the few hundred range to disperse every source in the field. The red grisms are tuned so that hydrogen alpha falls neatly in band from roughly redshift 0.9 to about 1.8, exactly the era when the standard ruler is clean and the cosmic acceleration has taken hold. Multiple dispersion angles and repeated visits are baked into the plan to pull apart overlapping spectra in crowded fields. Instrument papers, written after commissioning, place real numbers on that intent, resolving powers around 400 or higher for compact sources and a field of view matched to the visible camera, so imaging and spectroscopy share the same sky. And we have already tried the ladder on real tiles. In the quick release, the spectroscopic pipeline's redshifts in the Euclid Deep Field North were compared against high-resolution ground measurements in the designed redshift range. When hydrogen alpha is in the passband, the dispersions are small and the bias is modest, encouraging. Very practical confirmation that the clustering and redshift space distortion experiment can be built from flight data, not just from forecasts. The same note of caution appears in the release literature too. Interlopers rise outside the designed range. Overlaps must be controlled with geometry. Selection must be tuned. That is rehearsal, as it should be. With that plumbing in place, the parameters finally have a stage. We write the dark energy pressure as an equation of state W, of A equals W naught plus WA times parenthesis 1 minus A parenthesis, a two-number map that asks whether the data really prefer the calm point where W naught equals -1 and WA equals 0. Beside it, we place a gravity check, the growth index gamma, near 0.55. For Einstein's gravity, married to a cosmological constant, and one of the first places a long-range modification of gravity might whisper. Those are compact, honest summaries of a very large conversation, and they are exactly the summaries a survey like Euclid, built for geometry and growth at once, is designed to sharpen. The cadence matters too, because precision grows with area, and the map is widening in deliberate waves. Routine science observing began on Wednesday, the 14th of February, in the year 2024. By the time of the quick release, Euclid had already observed, on the order of 2,000 square degrees, roughly 1/7 of the eventual extragalactic footprint. The next landmarks are written down publicly. A second quick release in late June of the year 2026, and the first full cosmology data release on Wednesday, the 21st of October of that year, with order of magnitude more sky, something like a few thousand square degrees flowing into the joint fits. Put simply, rehearsals now, the first performance with the full orchestra then. And while the dark energy parameters are the destination, the road is already strewn with treasure. The first quick release gave us hundreds of strong lensing candidates, a first visual morphology catalogue of hundreds of thousands of galaxies, and a popular press description that reached for the right word, treasure trove, without hyperbole. That is what a wide, uniform space telescope can do, give you exquisite, fair pictures at a rate that turns rarity into statistics. Whether you care about bars in disks, ultra-cool dwarfs in the deep fields, or arcs that curve starlight into rings. The point for cosmology is calm. Every one of those catalogues also strengthens our control of selection, redshift, calibration, and instrument character. So yes, with Quone we can already practice the compression, land a provisional point in the W0AA plane using only the cleanest linear scales, and sketch the band for gamma from redshift space distortions and from the shear power, knowing the real verdict will come when the atlas expands. And because Euclid looks with one set of eyes and one discipline across the sky, the geometry that distances prefer and the growth that motions and shear prefer will be read fairly in the same voice. In our next step, I want to lift that point off the page and lay it on a real patch of the cosmic web, one of Euclid's newborn mass maps from the deep tiles, and let you feel how knots, filaments, and voids together conspire to give us distances, growth, and the first truly three-dimensional sketch of the dark that holds the luminous together.